Hey, what's going on, guys? xiangqi here. In this series, we're going to be programming the game of Go as developed by Jonathan K. Millen in April of 1981. So he sent his engine, well, it's not an engine, just a Go playing program to the Byte magazine. And there was an article published in that magazine. Here it is. I've been demonstrating this and walking through what exactly it does in the previous intro video. There was a big 40 minutes intro video, so if you're interested, you can have a look at that. And we're going to be focusing at reconstructing the pseudocode that is available within this article, which is available here. So here is a pseudocode for the entire game. Implementing both the board representation, like the rules of game, and a very simple AI. And this, despite the fact that the AI itself is really miserable in terms of strength, still it has a very elegant routine to count the linked stones, so the stone groups, and this is absolutely essential. And this is the smallest and the most elegant implementation I came up with so far. So because of sticking to this exact exact way of counting the captured groups of stones, which is one of the most important things, we need to define the proper board representation. So in this video, we'll create a board. We're going to be going for an array-based board representation, and then we'll encode the pieces and write the routine to bring the board, and we'll have a look why there might be many different it's not piece types, but the pieces might be marked with the different numbers. So I'll now jump straightly into the explanation of exactly what is that going to be. But before that, let me highlight another little thing. So I'm using the GUI that is called Sabaki. And later on, I really hope to connect our engine, the initial version, but the former versions, the next versions of the engines. Probably it's going to be a good idea to connect to the GUI. And they are very similar to the UCI engines in chess, but here instead we have so-called GDP engines. I'm not sure yet what the GDP stands for exactly, but they have the text-based interface just like the UCI did. Just the syntax is a little bit different. And here is the list. Here is the list of engines, including the famous Lila Zero that actually can be played within this GUI. So that's another step just to consider this connection to the GUI in the future. For testing exactly the AI itself, because it would be like before, like playing versus human versus another engine. So this might be on the cards later on within the project. Not the major step anyway. And another essential thing, why am I talking about this, is because of the board notation. So there are quite a few ways of how one can provide the board notation, and the way how this is done in the games and the tournaments in different countries, like in China, in Japan, in Korea, they might be a little bit different. The systems are a little bit different, but we're going to be sticking to this so-called GDP protocol. And here you see like the notation is almost like in chess. So we have 1, 2, 3, 4, 9. So for 9 board, for instance, and A, B, C, D, E, F, G. And for some reason they skip the I. So instead of I, they go for J straight away. I'm not yet sure why exactly that is happening. If anyone is aware of that, please let me know in the commentaries. But anyway, so when the engine wants to make a move, he says like this in algebraic notation, just like in chess. But since we only have we have the only square where the stone is going to land, it's literally enough to make it like this. So we're going to be sticking to this chess-like notation. I'm not sure yet about this J and I. Probably I need to use J instead of I, but anyway. Another point in regards to the board size. So, like in Go, there might be different board sizes starting from 5 to 5, then 6 to 6, 7 to 7, 8 to 8, 9 to 9, like 13 by 13, 15 by 15, 17 by 17, 19 by 19. So, actually, what I've realized so far in regards to this professional engine, so they do handle the board size automatically. For now, we'll stick to 9 by 9 board, which is actually not exactly what the original engine, which is called Wally, by the way. It's not exactly what the original engine by Jonathan K. and Millen did. However, still, like the last board you have, the smaller board you have, the more chances for an engine to play a better game, because on the large boards it's really getting complicated, because engine can win a local tactical battle. However, when it comes to the general strategic plan, it might turn out that it messed up completely and not going anywhere, just losing the scores, losing the territory. All right, so this is regarding the intro. Now we'll have a look at the board and what exactly we need to implement in regards to the board representation and stone encoding. Okay, so let's have a look at the board. So here I go to select tools, and let's get started. So we have black stones and we have white stones. This is pretty miserable amount of data to encode, right? However, here is where the complications are arising. So what we eventually need to do is the following. So let's say if I just started a new game and just try to play some weird moves. So for instance, okay, yeah, so like this, for instance. So this is horrible from the perspective of the Go, but anyway, like this, for instance, here. And now, if I place the white stone right over in here, what happens next is this, these stones are going to disappear. Now you might be wondering, why is that happening? Well, that's because this group of stones doesn't have what is known as liberties. So here is one example. So we can use the edge of the board in order to do this. So if the black stones didn't have any liberties, they get captured. Another scenario might be if I can actually drop back like this. Another scenario, you just imagine a group of stones like this, for instance, and like this. Here we have exactly the same scenario. So now black stones get captured as well. But you might be wondering, how on earth are we going to be implementing this? And this is the most essential thing that we actually need to implement. So let's drop back to this to the board editor. So I just started a new game here, and going back to the editor, stone tool. So here we got a stone, and in order to make this stone stay on the board, keep occupying this certain piece, it needs to have at least one liberty. So liberties are these kind of squares that are empty in terms of, like, they are not occupied by the opposite color stone. So for instance, if we have it like this, so how many liberties does the black stone have? It has one liberty, right? So for instance, if we just here, it has two liberties. So again, like if we have just we just place the stone on the board, it has 4 liberties. Yeah. If we put a white stone near, then this stone would reduce the number of liberties by 1. So now we have only 4 liberties. Now, for instance, if we place another stone here, then it takes another liberty away. So in case if we have only one stone here, then we could have say if up square there is a white stone, left square white stone, right square white stone, and down square there is a white stone as well. In this case, we know that this group is captured. But how do we know if we need to do the same thing but for the group of squares, for instance, for the group of stones? So here, let's say we have a group of stones, and we need to define liberties for this kind of group. So we're going to be doing this recursively, and that's the matter of the count variable, but we're not about touching this in this video in particular. We just need to get done with the board representation. So the convenient way of how to mark the liberties is to use a certain bit, and as well as we're going to be using the certain bit for marking the squares, so whether the square has already been counted as the part of the group or not. So for instance, so this this kind of like these stones are the part of the group. And by the way, if the stone goes here, for instance, so this is not a group. So group is only those stones that connect orthogonally. If the stone is connected diagonally, it's not connected actually. It's separated. So we need to find all the orthogonally connected stones. And in order to represent this kind of triangle here, we're going to be using another bit. So just trying to give you an idea what kind of features of the board are we about to be distinguishing, because this is absolutely essential, right? And also we have the off-board squares, because for instance, in order to capture using the board edge, so we imagine as there are the stones that take away the liberties, no matter the color. So it's not the empty spaces on the edge, on the board edge. So they like off-board squares or off-board stones, doesn't matter. So the idea is that if you have a stone, for instance, here, then it only has two liberties. So so here it doesn't have a liberty down below, and it doesn't have a liberty on the left. Same goes if in this case, so here we have three liberties, but no one here. So if we put white stones here, this stone is going to get captured. This is absolutely essential, and it took me quite a bit of time to understand the rules themselves, because yes, as a player, it's, for me personally, this was a real challenge. But anyway, so I hope you get an idea of what exactly we need to represent on our chessboard. So bearing this sort of a thing in mind, we can now go to the implementation, and now we're going to be writing the very first lines of code. All right, so here I have a table for piece encoding. So we have 0 representing the empty square on a board, 1 representing black stone, 2 representing white stone, and please have a look at this binary representation. This is essential. Now we have the stone marker, so that bit that would be used in order to count the stones recursively within the group. That's the group. Again, the group is the stones that are orthogonally connected to each other, right? Then we have, well, 7 is just the constant for off-board square. I believe this might be whatever, so for now it doesn't matter that much. And the liberty marker are also, so we're going to be bitwise ending the empty square with this bit. Again, so for now, at the current state, it just would be the matter of having the 8 for where the liberties are. But anyway, so I'm using this bits for because if later on it would be needed to go for more extended for more advanced evaluation, this might become on the cards. And now, for instance, if we want to encode the black stone that is marked, so that has been counted as part of the group already. So to avoid count this again, the next iteration, in the next recursive call. So here we have this bit 4. Select this bit 4, bitwise ORed with the black stone. So we bitwise OR this with this. So 4 bitwise OR with 1 would be 5. So this bit becomes 1, right? And here is the 5, right? This is 5 in binary. This is 5 in decimal. And same for white stone. So for instance, we have for white stone. So we have this bit, and then this bit is the stone marker. So here this bit is equal to 1 after bitwise OR with this one. Then we have 0 1 1 0 0 1 1 1 0, which is 6. Right, so hope this makes sense. So probably let's start by encoding this some of the constants. So we have the black that is equal to 1. We have the white that is equal to 2. Let's say selected. Let's call it selected stone. This is gonna be equal to 4 stone marker. Liberty marker. Yes, I just call it marker, and this is gonna be 3. No, sorry, 4. Stone marker is 4. All right. What else? So, oh, sorry. Then off-board is gonna be equal to 7. Then liberty is gonna be equal to 8. All right, and for now, and we actually don't need to encode this ones because they would be this byte is going to be bitwise ORed during the count routine working, and by the time then when the count routine would end up working, we get the count of stones, we get the count of liberties. That would be the data structures to keep those. And after we answer the questions whether the group has been captured or not, we then reset everything. So we just bring the board to the state like without dropping back this marker for stones, dropping the markers for liberties as well, and we initially would only have empty spaces, black stones or white stones, and offboards are not going to be changed there as well. All right, so now it's time to define the board array. So again, later on, this might be on the cards to have different board arrays, board sizes like 9 by 9, 13 by 13, 19 by 19, and so on. But for now, for simplicity, we'll stick to this 9 by 9 board representation. And probably we can define the board size variable. So let's call it size. Let's call it board size. So we would be sticking to yeah. So 9 should be just okay for now. And then we'll just probably have many board arrays and one pointer that would be pointing to the specific one, like board like 9 by 9. And then like we'll say that board is equal to board 9 by 9 during the initialization. But for now we don't need this. So for now just we'll do it like so. So the only parameters to change would be the board size for all the loops, like bring the board counting and all this stuff. And yeah, so anyway, now we also need to bear in mind that we want to encode the offboard squares. So to have the 9 by 9 boards, we need to add we need to add 2 elements on the sides and 2 elements on top and bottom. So eventually 9 by 9 with the offboard lines turns into 11 by 11. So let's have a look how it works. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here I have 7 means offboard, so I'm working the offboard line. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? And here I just put zeros because these are the empty squares. So here is our go ban or the go board, and now we only need to copy this part. So copy, paste, 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 paste. So 1, 2, 3, 4, 5, 6, 7, 8, 9. A bit more, a bit too much. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and this should be the last one. So this is not on the cards again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so we have 11 by 11 board array here. Okay. Next thing to consider, we need to encode all this black, white square, the marked squares, and the liberties, and the offboard squares, potentially might be on the cards as well, to be represented by the ASCII characters, because it's easier to visualize the board when we're going to be printing this to console when the stones are marked with the human readable characters rather than just the pure codes, because we can forget about this. I just create the pieces variable, and this is going to be a string. And now what we have, so if index is going to be indexed by 0, so we have board, so for instance, let's say we have the board indexed by the square. The square is equal to, for instance, this square, right? There we have the value of 0. So if we index our pieces by this board square, then this is going to be 0. So pieces indexed by 0, and we want so we're using this the value on the board as the index to index the pieces array to return the specific character, ASCII character we want to display on the board. So here I want to represent the empty squares with the dots. So I just want to do this like so. Then for black, for unmarked black stones, I want to use the hash symbol. You may use whatever you like, doesn't matter. For white stones, I want to use the O symbol. 0, 1, 2. So it just goes like 1. here just goes 2. So here is the black stone unmarked, here is the white stone unmarked, right? Then there might be some marked stones. So you remember this one. So 5 and 6. So let's count. 0, 1, 2, 3, 4 are skipped. Then 5 and 6. So for instance, the marked black square, black stone would be treated as B, and the marked white stone would be treated as W, right? So 0, 1, 2, 0, 1, 2, 3, 4 are skipped. 5, 3, 4, 5, 6 are this. Then 7 offboard. So offboard we can mark as X for now. Then we'll just drop it to the space. But for now, let's make it X. And the liberty is gonna be 8. The 8th is, let's just make a plus here. So it's quite nice to have it like this. Okay, and now let's create the very first routine, the print board routine. So def print board, and also let me just add some commentaries here. So this is board. This is the go ban board. These are the stones, right? And these are the ASCII codes, ASCII representation of stones. So yeah, hopefully it makes sense. Okay. All right. So we can go. Let's go the easy way of doing this print board. So let's loop over board rows first. In here, here is where the board size comes handy. So board size, literally what it is. Let's call it go ban size. So 4 row in range, and we need the range of the board size. So board size. All right, and also we need to loop over board columns. All right, so 4 column in range, and again the board size. So this already comes handy, because if we change the board size and the board array itself, then this print board routine should be working as well. So now we want to initialize the square. So initialize the square. Initialize the square. So square is going to be equal to row multiplied by the board size plus the column, right? And here already, let's just to make sure we do everything properly. So let's print the square. All right, so here is our tutorial. All right, so open in terminal. And by the way, I don't need this anymore, and for this video I don't need this as well. So let's go to the terminal. Yeah, I don't need this one either. So yeah, now to run this, I say python 3 wally 00.py. Here we go. I didn't call the print board function. Okay, so print board. So now I expect to see into the squares from 0 to the length of the board. And indeed we do. So 0, 1, 2, 3. Yeah, great. Now, next thing we need to consider here, we want to initialize piece or stone or whatever you want. So piece, or let's better call it stone. Stone is equal to whatever we have the board indexed by the square. Indexed by the square. All right, now here is the deal. So here is the deal. Well, actually, also here I want to print the new line, so just print with no parameters might be on the cards. And here I want to print the stone, but not the stone, but actually this pieces. Well, let's kickstart by the stone. So now we just see the bare representation. So stone at the end. I don't want to print anything. So let's have a look. Okay, something goes horribly wrong. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is because board size, yeah, actually the actual size is 11. So here we need to make some sort of an adjustment. So board size plus 3. All right. Or maybe to encode, well, actually I can just make it 11, but this might be unclear. This might be treated as 11 by 11 board. So how to call this better? Yeah, let's call it margin. So margin is equal, no, not 3 but 2. So 9 plus 2 is equal to 11. Yeah, I'm bad at math, I'm sorry guys. Okay, so yeah, margin is going to be equal to 2. And here maybe just do board size margin, and maybe just let's call it board range. I just want to simplify the code a little bit. So let's say board range is equal to board size plus margin. So just to be easier to code, board size plus margin. So board range should be 11. So here I just want to say board range and board range here, right? Okay, still something goes horribly wrong. So just want to print the board range. So this is 11, all right. Okay, and obviously here we also need to use the board range. And now this should be working nicely. Okay, here we go. So here we go, here is our chess board. Sorry, I'm sorry guys, here's our Go board, Go ban. All right, now let's make it, let's prettify this a little bit. So I want to say, plus I need to stringify this to make the string concatenation. So save. Okay, here we go, it's much better. So yeah, here is what we have on our board. So see like this, the stones are here, the off-board squares are here as well, but this is not convenient as been mentioned. So now let's map these values to the ASCII characters. So instead of using the stone, I can just say pieces indexed by the stone, and now we have this sort of a thing. All right, so far so good. So we have the black square, the white square, and this is the off-board squares. We'll skip the off-board squares. So the matter of skipping the off-board squares is just replacing the character like this. So we can go for this already, but yeah, for now let's just keep sticking to this. So what else do we need here? Wally.by what? Okay. Also, yeah, let's actually check if we go this, for instance, like it's gonna be 5, this is gonna be 6. So I'm testing the marked squares. Okay, so this square is marked, this is not marked, this is not marked, this is marked. And if we have the liberties, for instance, like this, here, and the liberties are the same for both colors. Yeah, here we got the liberty. So this comes incredibly handy when it comes to debugging. So when we're going to be debugging our count routine, so it would be just printing where whatever stone has been counted already and how many liberties we have. So we'll see this visually. This is going to be really handy. Okay, so this is nice. And since the encoding is working, the very last thing to consider is to print the rank as well. So here I want to print the rank. So let's say print row, right? So not exactly what we want, so I want to say if call is equal to 0 in this case, right? Now to avoid this new line, I want to say row and at the end nothing there, right? Now if we have a look at the logs of the GDP engine, we see that it should be 1 from below and goes to 9. So let's try and consider that as well. So here we have 11 minus row. Okay, but you see like 1 in this case starts from here, but it should start from here just visually. So if I say just 10 here, now it works, and now we don't want to print this one and this one. So and row is greater than 0 and row is less than 10. So here we go. Now the very last thing we need to do is just to get rid of this offboard squares. So let's do so, right? Yeah, it's nice. I just don't get where this. So maybe I just don't want to print this guy here, but here instead. Yeah, now it's much better. And now here, let's also say, so let's stringify this one. And plus, just want to make a little space. Nope. String. Oh, yeah, obviously here. All right, so yeah, now it looks like much better. Now let's provide also, let's provide by the end. So you want to print notation as well. So print and A, B, C, D, F, G, H. And for some reason they use J here, not the I. I'm not sure why exactly, but yeah. Maybe I'll figure this out later on. All right, so far so good. So let's give a new line here. Yeah, so we got our board and everything seems to be working just perfectly well. So yeah, okay guys, this is it from my side in regards to this tutorial. So we've just ended up with nicely pre-printing the board. We get done with the piece or stone encoding. So those have the black, white, those with the markers, the offboard squares. We've seen they were there. The liberties also working, and also we have the variable board size. Thanks for watching, guys, and see you in the next video. Until that time, and take care.